Hello and welcome to another homework help video. In this video, we'll be looking at the FFT function and how to get a single-sided spectrogram in Matlab. I'm going to be using the live editor and a live script to do this because it's very easy for me to show you some plots as we move through. First thing I want to do, and this is true for all of my Matlab scripts, is go ahead and say clear. And this function, if you don't remember, will clear out all of the variables in our workspace. I have those hidden off to the side for right now, and I'll bring them on screen later as we need them. The next thing I want to do is create a couple of variables that are very important for us when we do any of these FFT functions. And there's two things we really need to know. First is our sampling frequency. And I'm going to call this Fs, and for the purposes of this video anyways, we're going to kind of make up a little bit of data here. So I'm going to just make this sampling frequency 200, and I want to add a comment here, and I'm going to say that this is the sampling frequency in hertz. With real data, you would need to know the sampling frequency at which your information was collected. Here, we're going to create some synthetic data, and I'll show you how to do that in a little bit, and we get to set our own sampling frequency. This is really handy because, as you'll see later, sampling frequency has a big effect on how the FFT works. The other thing we need to know is the length of our data. Now I'm going to create a variable, and I'm going to call it len, length of data here. And I don't want to use full length because you will see that it comes up as the length of the largest array dimension. That's a specific function in Matlab. So I'm going to use len, which isn't a specific function. And I'm going to say that we've collected maybe 100 samples of data. So this is the number of samples we have collected. And from here on out, I'm going to try and keep the comments a little bit more brief so that we can fit them on screen for you. All right. This is the only thing we really truly need to know for any data set that we want to take an FFT of. We need to know the frequency at which it was sampled, and we need to know the length of the data set. If this is a data set you're importing, you can actually use the length function directly inside of Matlab to figure out the length of your array. This would be the number of samples that you have. And I'm going to just come up here and say, this is required setup for our FFT. Great. And I'm going to come down, and now I'm going to just make a new section for us here. So I'm going to kind of come in and I'm going to add a section break, and this is going to be a very special section. I'll comment this. This section is only used to make a signal we can use for this example. Normally, you would import your data here. All right, so now we have a section that's only used to make a signal. We can use this for our example. We can use this for our example. So there's a section only used to make a signal. We can use this for our example. Normally you would import your data here. Great. So how do we make a fake signal, and why am I making a fake signal? Well, this quote-unquote fake signal is going to be really useful for us because it gives you an idea of what our frequencies and what our amplitudes should actually be. If I were to import raw data, we might not know what these values should be, and it kind of obscures some of the effects of things like sampling frequency and length of the data signal later on once we're plotting our FFT. So I'm going to keep this here for an example as opposed to importing some raw data that we don't know anything about. Of course, most of the time if you're using an FFT, you would be using this on raw data. The thing I really want is a signal, and I'm going to call it signal, and this is my signal, and I'm just going to make something nice and simple. So I want an amplitude of 2, and we'll do this as sine, and of course sine in Matlab is done in radians. I want to give you things that are visible in hertz so that we can kind of directly match these things up. So what I'm going to do is I'll do my 2 pi, and of course it already knows, right, that pi is a function, and this is going to be my frequency. So I can use 10 hertz, and I need a variable t, 2 pi t, or 2 pi 10t, sorry. I would have, for any value of t that I've given this, I would have a number that is the corresponding signal. So this would be my time and amplitude on a regular sine plot. Now I want to add a couple of these things together. This signal is comprised of 2 times sine of 2 pi 10t, so amplitude of 2, frequency of 10 hertz, amplitude of 14, frequency of 7 hertz, amplitude of 15, and a frequency of 70 hertz. And you might think to yourself, well, this is really easy to comprise a spectrogram from these 3 signals. I could draw this by hand, and one of my previous videos would show you how to do that. But I like this because although we may not in reality know what this signal actually is comprised of, it gives us a good idea, something we can kind of play around with in this example. And for right now, I'm going to change kind of the layout. I'm going to say I want a plot layout in line over here just to kind of clean things up, so we have a little bit more of a view of our code. Now, in order for this to work, I have to give Matlab some value of t that I want it to evaluate for some value of signal. So I need a bunch of data points that are signals. So I need my array of signals. And to get that, I can give it an array of t, or I can make t be an array, and it will automatically compute every value of signal for every value of t in my array. So what is t? Well, t happens to be the time that we wish to evaluate this entire signal at. And for a given sampling frequency, that t would probably be in steps of my period. So the very first thing I want to do to create some synthetic data here, again, is just creating some synthetic data, is I need my period. And I want my period to be equal to, well, 1 over my sampling frequency. By definition, that is the period. So 1 over fs, and I'm going to, very clearly state this. This is my period. Then I need to create an array that is t. So all of my individual times that are comprised somehow of this period up here. And I need to know how many of these I want. Well, normally I would have some length of data. I have a length of data up here, so I want to make probably 100 values of t that are equally spaced out at my period. So to do this, pretty easy, I can ask Matlab, and this is a little bit of a trick if those of you that don't know it, for kind of creating some arrays, can ask Matlab to start at 0, and what I want you to do is to move in increments of, so my way of saying that is I want you to count in increments of 1, and if I left this without the 1, it would kind of choose that increment by default. So I want you to start at 0, count in increments of 1 until I get to L, and this is where things are going to get, or my length. complete that, my length, this is where things are going to get weird, minus 1. And where does this minus 1 come from? Well, if you remember, MATLAB always starts its index being where the first position of the ray is counted from, at 1, unlike most programming languages that start at 0. So this is going to go from 0 to the length of my signal, in this case 100, minus 1 spots. So this is going to start at 0, go from 0 to 99, because it will go 0, counting in steps of 1, to 99. So 0 to 99 means that I will have exactly 100 values. So start at 0, go to 99, that gives me 100 values, and I want to multiply each of those by, quite simply, my period. So what will this do? All right, if my period is 0.2 seconds, then I'll have 0 times 0.2, which is 0, so times 0. Then 1 times 0.2 is 0.2, then 2 times 0.2, 0.4. So I will build this period, I will build this array of t, and I can actually check this really quick. I'm just going to suppress the output of this line. Actually, let's leave this unsuppressed. It'll output right here in the same window, and I'm going to run our little chunk of code really quick. And here we go, and I have a value of an array of t is 100, of course 0, 0.005, 0.1, 0.015, and this comes from our period, which is 1 over our frequency, and our frequency is 200, so this makes sense. 1 over 200 would be 0.005. Great, and I'm feeding these 100 individual variables in this array into this function here, so it'll compute these at position 1. Remember, we start counting at 1, position 1, position 2, position 3, and so on. And sure enough, 0, t is 0, well, everything that's multiplied by 0 is 0. Add my zeros together and I get an amplitude of 0. And then I multiply all of these by, or I multiply each of these frequencies by 0.005, so my time step of 0.005 seconds, I find an amplitude of 15.8 and something, then a negative 7.129, and I can actually plot these at this point. So if I was curious what this looked like, I could plot this entire thing, and the first thing I need to do is tell it what I want to plot it against. So I want to plot time, and I want to plot time versus signal. So there we go. Plot me time versus signal, please, MATLAB. I'm going to suppress the output of this line and this line so we don't have to look at the raw numbers. I'll hit run again, and sure enough, it should plot for us. Oh, great. Beautiful little plot. So this is our signal that we're starting with. Here we go. You can see some low frequency component in here. This is probably our 7 hertz component, then maybe a little bit of a higher frequency at 10 hertz, and then something much, much higher at 70 hertz. So there we go. And for right now, I'm also going to kind of comment out our plot because I don't want this to fill up our screen. We know what our signal looks like, and we're pretty good with that. I want to start another section here. This is going to be our new section, and this is where we're going to start doing the FFT. This is where the work is going to happen. So perform FFT here. All right. Perform FFT here. Okay, great. So, how do we do this FFT? Well, it's pretty simple in MATLAB. All we need is some variable that we want to be our container for this. Let's see. I'm going to use, call it SFT. So this is my function, my signal FFT. Actually maybe SFFT. There we go. Signal FFT'd. And now all I need to do is tell Matlab I want to take the FFT, and this is, like many programming languages, a built-in function. So I can just say FFT, and it will ask me, do I want the fast Fourier transform? In fact, I do want the fast Fourier transform. And what do I want it of? Well, in this case, I want it of my signal, and you'll see that you can give it n in dimensions. You can give it the length of the signal you want to use, and if you have it in some multi-dimensional array, you can say which dimension of that array you want it to take as its input. Here I just need my signal, and that's going to be sig. And you'll notice that I'm not giving it any sort of information yet, or I'm not really doing anything yet with either the frequency of my signal or the length of my signal. And this will come back once we want to recompose our output of our FFT and we want to plot that. Part of the function of that FFT, remember, is to sort of interrogate our signal. It is going to ask this signal, whatever it might be, this data set, whatever it might be, how much of a specific frequency exists within that data set. And it's going to keep asking more and more questions of how much frequency exists within this data set. What it's going to return over here is an amplitude of both the sine and cosine strength for every frequency that it interrogates our signal with. So it might start by asking how much 0 hertz signal is in this variable, and that would be akin to asking how much of a DC offset does my signal have? Am I shifted up or down? This signal is right around 0, and we can see that I haven't added any shift anywhere in here, so we would very much expect that if we asked this how much of a 0 hertz component is here, we would get a value of 0. If we asked how much of a 1 hertz component is here, we would probably get some value fairly close to 0. So there wouldn't really be any sine or cosine component. As we go up, we might ask it, how much 10 hertz component is in this signal, and it would return, in theory, an amplitude of 2, and that would be in the terms of sine. The other thing that's worth remembering is that this FFT, part of what makes it so efficient is doing this in the complex domain. So this is going to return for us a real component, which is our sine wave amplitude for some frequency, and an imaginary component, an I value. And that's going to be kind of the cosine component. If we were really interested, we could back out our phase information. So if one of these signals had a phase shift to it, or one was perhaps a cosine, shifted 90 degrees out of phase, we would see that shift as a difference, something we could compute anyways, between our real and imaginary component. So what I'll do is I'll leave this kind of unsuppressed, we'll run it, and we'll see what we get for a data output here. So again, I suppress this plot, and sure enough, look at this, we get a very large, here it is right here, we get a fairly large data set, 100 data points, which is interesting because we got out the same number, right? The same number of data points as the size of signal. And that's going to come back and tell us something a little bit later that's kind of important about this FFT. Now, if we look at what it came back with, we'll see that our real components seem to have some value to it. Our imaginary components are effectively 0. There really isn't any cosine component at any of these frequencies. And you might be wondering, well, what is the frequency that represents this amplitude? And that's some work we have to do for ourselves kind of coming up here in the next couple of steps. The other thing worth remembering, and there's a lot for this, is that this is giving us kind of that two-sided spectrum. So because of the natures of sines and cosines being symmetric functions about 0, we have this effect where we kind of have a mirrored image down the middle of our frequency spectrum. In other words, if I am asking this to give me a 0 to 200 hertz range of frequencies, right? Which is what I will ask it to do a little bit later. That means that right around the middle of this data set, I will have a mirror image. Also means I can only really resolve signals up to half of my sampling frequency. Now, we're not going to go through the time here to plot the two-sided FFT, the two-sided spectrogram or two-sided spectrum, because it's not really something that we normally use in mechanical engineering. Generally, our interests lie more in the single-sided spectrum. Before we can begin moving to our single-sided spectrogram, one of the things that we want to do is to get rid of this kind of imaginary component. We really don't need this. We're more focused on just the real component, right, of all of these frequencies. We want to know the real component, the amplitude of all of these frequencies. By convention, this is really truly the cosine component for all of these. And fun little trick, we can do that by taking the absolute value of a complex number. So if you take a complex number, you take the absolute value of that, you only get back the real part of that number. And this is a very easy thing for us to do in Matlab. So let's create a new variable here, two-sided FFT, and I'll call that'll be my new variable. Let's see what MATLAB's complaining. Might be invalid MATLAB syntax. I don't think it likes me having the two out front. Of course it doesn't. Two, and we'll camel case this so it's a little bit easier to read. Sided FFT. So I have a two-sided FFT, and to get that I need to take the absolute value of my signal. And if you don't believe me, when I run this, it should return just, and there it is, just the real portion of this. But you'll notice that this number, this real portion of this number, is not this value right here. So something has gone wrong. It has somehow gotten scaled. And the easy way to fix that scaling is to divide this all out by the length of our signal, which I believe is our LEN, our length of our signal. So what happens in the process of getting rid of this imaginary component is that our signal gets scaled by our length. So if we divide all of these variables, all of these values, this 1.2681, by the length of our signal, we undo kind of that scaling that was done, and I'll rerun this, and sure enough, we are right back to where we started, 1.2681. So this length helps us scale back this absolute value function of our SFFT variable. Great. So now we have a two-sided spectrum, and we could plot this if we wanted to. It would be kind of meaningless without calculating the frequency, and maybe if we want here, let's just try and see what we get. It's going to be a little bit ugly and not really very helpful, but we'll give it a try anyways and see how this looks. Now, I'm going to suppress these so that we're not kind of filling up the screen with just errant data. And sure enough, not great, but you can see what I mean by this thing being reflected. And granted, this isn't in any sort of frequency values, right? This is just plotting the data point value versus the actual data point, but it's good enough for us to see that this whole thing is kind of mirrored about the center. This upper half here is a reflection of the data down here. And again, that's a function of the whole way the FFT works. We can also sort of start to see something interesting, where if we look at even these amplitudes, we notice that although this is mirrored, these amplitudes don't quite make sense. I have an amplitude here that is, give MATLAB a second to think. I have an amplitude here that is a bit lower than what I would expect it to actually be. So I have, and again, we can kind of ignore the x variable right now, or x value right now, but I have an amplitude that's 7.5, and I would have expected something maybe around 15. So I've gotten kind of double the amount of peaks, but half the amplitude for each of my peaks. So I have two things right now that I need to fix. First, I need to fix my amplitudes, and that's something that's pretty easy for us to do. So I'm going to make a new variable, and I'm actually going to get rid of this. I'm going to comment out this plot for right now, because again, this is something that we're not really concerned with. It's just there so that you can see kind of this process as it unfolds. Single FFT, I'll call that my new variable. So this is my single-sided FFT, and what I need to do is to take just the first half of this data. So basically everything up to the first chunk of this data. And since I said this is data points, right, you'll notice there's 100 data points. So I need to take from data point, well, from really data point 1, which is out here, all the way out to the middle. And this is, again, where Matlab tends to get a little bit confusing. So I want my two-sided FFT. So all of this data, and I can ask it to give me certain portions or to iterate through this variable. And the easy way to do that is right next to the variable, I can say, I want you to start at a specific position, in this case, index 1. So index 1, start at the value in the first position, and I only want half of your data points. So I have some number of data points, my length of my data, and I want half of the length of that data. And I think, you know, you might look at this and intuitively go, great, this is all I really need. I'm going to go from data point 1, and the length of my data in this case is 100 samples. So I'm going to go from data point 1 to data point 50. The problem is that data point 50, right, contains not 50 hertz, but it contains 49 hertz. This first data point in this array, this two-sided FFT array, contains 0 hertz. And that's a really special number for us. That 0 hertz, again, is kind of the mean of our signal. So we do want to keep that. We definitely want to keep that. And we want to keep it as is because it comes out of the FFT, it is the mean of our signal. And if that's the case, this is 0 hertz, that means at data point 50, I have 49 hertz. I have the value that corresponds to the amplitude at 49 hertz, not 50 hertz. So I need to grab one more data point than what I would expect to need in order to get, well, now I'll have 51 data points in total, but I'll have the value at 1. I'll get 0 hertz, and then I'll have 49 plus 1, so I'll have my 50 hertz. So at data point 51, which is what I'm going to get here, I will have the value, the amplitude, that corresponds to 50 hertz. So let's comment this out. I'm just going to suppress that, and I'm going to run this really quick, and we'll come down and kind of get this. And I actually can look at what I'm getting back. And if I kind of hover over this, you'll see that I'm getting, sure enough, I'm getting my first data point at 1.2681, and I'm getting 51 data points from there. So this is excellent. This is exactly what I would want out of this entire thing. Now, this also tells us one other kind of interesting key rule about the FFT. And this is a really useful rule to notice. What would happen if length were an odd number? Well, if I made length odd, and I divide an odd number by 2, something really weird happens, right? Matlab has to suddenly make a decision at where it is splitting this value. So I could get, remember this is an index number in the array, I could get an index number that isn't a whole value. And an index number that isn't a whole value doesn't exist. So Matlab would have to kind of intelligently pick, or perhaps it would even throw an error. And, honestly, we can try that. Let's make our length 101, and we'll run this. And sure enough, actually, here we get an error, a warning this time. Integer operands are required for colon operator when used as an index. Basically, what it's saying is that I don't know what to do with this length. I'm not sure what I should have here. And it's going to kind of only be a warning because it's going to try and make an intelligent choice for us. But this should be a key to us that what we really want going forward, if we want to be able to split this FFT down the middle, is we want our sample length to always, always, always be an even number, right? Even if I make this 102, and I run it, still good, no error. So as long as this is an even number, we are good to go. This means sometimes you need to check your data, so this would kind of be down here if we weren't faking our data, right? If we weren't building some synthetic data. One of the things we might want to do in here is check to make sure that the length of our data is actually even. And if it's not, we'll choose to chop off the last data point. It's one data point in a many, so it doesn't really affect our output very much, but we can chop off the last data point to make sure that our data is an even length. Great, so now we have our single-sided FFT. We have figured out that we have everything from 0 to half of our frequency band, so 0 to 100 hertz in this case, since my sampling frequency is 200. I have 0 to 100 hertz, and again I can only resolve half of my sampling frequency, so the Nyquist frequency, if you will, is the rule that applies here. And the next thing I need to do is to multiply all of these amplitudes by 2. If you remember, when I plotted this, pop this guy out. I'll go back and really just quickly plot this again. Oh, not my signal, sorry. I will plot my two-sided FFT again. Let me suppress that. Plot my two-sided FFT again. My amplitudes, right, are mirrored, so my peaks are double, but my amplitudes are cut in half. So I need to multiply all of my amplitudes by 2. But remember what we said about this first data point, this very first kind of index in the array. That contains 0 hertz, my 0 hertz frequency information, so the mean offset. And that just comes out as the mean offset. That's part of the FFT. So we don't have to do anything with that information. So what I want to do, right, is I want my single-sided or my single FFT here, and I'm gonna tab down. Actually, I should really good practice. I should add a comment here, a real quick comment. Take the single-sided FFT. So I'm going to cut this in half, get my single-sided FFT down here. I need to scale that. And this is going to look weird maybe at first, especially if you're not used to kind of seeing this type of syntax in Matlab, but follow along and I think it'll make sense. I want to go from index 2. So this is my index because I have this right next to a variable that's an array. So I want to go from index 2 to the end of my array. So 2 to however many data points are in the single FFT. I want to go from 2 to the end. And I want to fill that up with 2 times, and this is going to be times the data in single FFT, but only at index 2 to the end And this is skipping, you'll notice this is skipping index 1, right? We don't have 1 here, we have 2. So this is skipping index 1, which is skipping our 0 hertz. So this is starting with index 2, not index 1. It's skipping 0 hertz, and then everything after 0 hertz, it multiplies by 2. And it doubles this value. And we can kind of check this out real quick. I'll let it output this line and output this line. We'll run this guy really quick. And we start at 1.2681. Sure enough, 1.2681. So this is our 0 hertz value. And then if we come over and we look at our next value, our next step in frequency, and notice I say step in frequency, I get 1.3813, multiply that by 2, and I get 2.7626. So sure enough, it is multiplying everything right along by 2. And this is exactly what we want. So now our amplitudes, with the exception of 0 hertz, which we don't need to touch, have all been multiplied by 2. So this scales my FFT up by 2. All right, so there we go. So now this scales my FFT up by 2. This is really useful for me. Now the last step I need is to create sort of the correct frequency values to plot against our amplitude. And what we have to remember is that for each data point in time that we collect, so in this case, I think if I scroll up here, right, we've collected 100 data points. So for each data point in time that we collect, we get that number of frequency values, frequency chunks back. And the proper term for this is the right number of frequency bins. So in other words, we get bins that we can fill with amplitude, and we get the number of bins back as the number of data points we put in. Which means that if we take, as we have here, right, 100 data points, then we get our sampling frequency chopped up, the sampling frequency that we started with is 200 hertz, chopped up into 100 little chunks, and these little chunks are the bins, which means every amplitude that we look at coming out of our FFT is 1/100th in this case, or 1 divided by our length, so 1/100th in our case, of our sampling frequency. So I just want to try and say this in simple terms. So I have some frequency after the FFT, so frequency after the FFT, and that is our sampling frequency. What did I call that? Fs up here. So that is our sampling frequency, Fs. And I said that's kind of 1 over n, sort of 1 over the length, or whatever step it is, over the length of our data. So kind of, if you want to think about it like this, right, we would start counting this entire thing at at 0, right? So we would do like 0 over 100, and we would kind of find out that that's 0 steps, so 0 hertz, so that would get stuffed in there. And then maybe we want to evaluate this again at 1, so 1/100th, 1 out of 100 chunks, 100 bins, the first out of 100 bins times our sampling frequency. So now maybe we say, okay, great. So now we do 2/100ths times our sampling frequency. So you can kind of imagine what these steps are going to look like. The problem is, right, I'm manually changing this from 1 to 2, or 0 to 1 to 2 to 3 to 4. And I want something that will do that for me. And I can create kind of this just array of numbers by starting at the number 0. And I know this looks like we're indexing something, right? It looks like we're going to index a variable, but since I don't have a variable name out in front, Matlab is going to make all of these kind of this array for me to the size I want. So I want to start at 0, I want to go in increments of 1, and how far do I want to go? Well, I know I only have kind of half of all of my data points. So I need to go to whatever my length is, let's see, 100 divided by 2. So I need to go to 50. So I want to make a set of numbers that go from 0 to 50. 0 to, I don't want to hard code this, so 0 to L divided by, or length, our length divided by 2. So what this is going to do is it's going to start at 0, 0, there are 0 out of 100 bins, times our frequency is just 0 hertz. The first 100th of our bins will be 100th of our sampling frequency, so that will be the next value, then 2, 3, 4, 5, 6, all the way up to half of our length, or 50. And if I run this one, you'll see that sure enough, I start at 0, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And these are the frequency bins in hertz. So 0 hertz, 2 hertz, 4 hertz, 6 hertz, 8 hertz. So what happens to 7, right? What happens to 5? Well, those values get weighted to one side or the other of the spectrum, which means if I had something that fell right at 7 hertz, here its contribution has to go to one of these. And there is a direction in which it actually goes. I don't want to spoil the surprise, but it's kind of interesting because if we had something that fell at 7, we don't, right now, maybe, depending on your math knowledge, you might not know, does it go into this 6 bin or this 8 bin? Okay, so I remembered to come back here and swap this length out, make sure that this matches, right? I don't want to hard code this in because what I'm going to want to do here in a minute is change the length of my signal. But, we have our amplitudes, we have our frequencies. Ideally, everything makes sense. We're gonna have 0 hertz, so frequency times 0, all the way up to frequency times whatever our length is. I suppressed my outputs here, so we don't have to look at that. And I'm going to plot my FFT. This is going to be great, right? So I want to plot my frequency FFT here versus my data, my single-sided FFT here. And again, I should probably comment this sucker right here. I should probably just comment this line. This creates the frequency for my FFT. All right, this creates the frequencies for my FFT. Okay, let's see what we get when we plot this. Whoops, that should not be capitalized. Now let's see what we get when we plot this. Here we go. And, well, this doesn't look right, does it? I'm going to zoom out here a little bit in our code, but we only have 2 peaks, so this peak is kind of ugly, unfortunately. Let me add a data tip here. And, well, that looks right. 70 and 15, it's occurring at an amplitude of 15, right? So we have an amplitude of 15 and some rounding error, but a frequency of 70 hertz. Here, a frequency of 6 hertz, an amplitude of 9.6 something. Well, we don't have anything at 6 hertz. We have something at 10 hertz, which we don't even see. We have something at 7 hertz, which definitely isn't 6. We have, our 70 hertz and 15 amplitude, that's coming out right, but this isn't. And even if we start to poke around, right, 14, 10, yeah, that's still not right either. And again, you can actually kind of see these nice jumps. Remember I said that this is going to be fairly large jumps, right? Because we're kind of dividing out by our length. So maybe we can see what happens if we make our length longer. If we make our length of our signal longer, we get more bins, right? We get more values to chop this frequency up by. So right now we're chopping this 200 hertz up into chunks, 100 little chunks. Let's see what happens if we chop it up into maybe 150 chunks. Let's try chopping this 200 hertz up into 150 chunks. So now each data point here represents one of those little chunks. And well, this is interesting, right? This is we do have a peak at 70 hertz, but it's gone wrong. It's gone all wrong. We're only at 9.7. That amplitude isn't right. We got something down here. Well, at least we have something close to 10, but that amplitude isn't right either. We got something... Oh, we're getting closer. We're like an amplitude or a frequency, sorry, of 6.6 hertz. And again, all of our amplitudes have gone wrong, but at least we're looking like we have 3 peaks. Might be the right direction. So maybe we're going to say, all right, well, clearly increasing our length gives us more discrete data points in our plot, which means finer frequency divisions or better resolution. So let's take this up. Maybe not that many notches. Let's take this up another notch. Let's make these equal. So now we have 200 hertz divided into 200 chunks. So if we have 200 divided by 200, each of these data points, now we can resolve things in our plot up to 1 hertz steps. So every data point, I'm not showing the data points, I'm plotting this as a line, but if I were to zoom way in, this line is made up of points, data points occurring at 1 hertz steps. 200 divided by 200 is 1. 1 times our frequency is 1 hertz, so we get 1 hertz steps, and let's see what we get. Well, yeah, that kind of makes sense actually, right? Because we're at these 1 hertz steps, now we can actually hit the frequency that we want. We want to check, so we want to check at a frequency of 7 hertz, and we get an amplitude of 14, and we check here, and well, we're at 10 hertz with an amplitude of 2, and that's right. This is great. This really makes a lot of sense. So we've kind of discovered something here, right? And let me kind of bring this back up. And I'm just going to click here really quick to pull this up. And 15, and 70 hertz we have 15. That's great. So we've learned that the more data we have, the longer the length of our signal, the longer we record data for, the better our resolution. And we at least want the same number of data points at a minimum as the sampling frequency we pick. So if we sample at 1 kilohertz, we minimally want 1,000 data points to resolve anything. But you might ask, well, is there any benefit from going higher? Well, let's try that. Let's go to 250 now. So we're going to chop this frequency, this 200 hertz, up into 250 chunks. And what happens now? Well, oh man, that went poorly again. Right back to something, like it didn't know if it was supposed to be at 69.6. Well, remember, these steps now are less than 1 hertz. I've split this up into bins that are smaller than 1 hertz, and it's kind of gotten real ugly. So this is an interesting sort of phenomenon. You know what? I wonder what happens if I make the length of my signal another whole multiple of my frequency. Let me make this now 400. So this is not just both a whole number, right? Remember we said we needed this to be a whole number, not an odd number, but a number divisible by 2, right? So we need this to be an even number, and now this is a multiple of this. It kind of happened before at 100 hertz. We got kind of close. At 200 hertz, it looked pretty good. I wonder what it's going to look like at 400 hertz. And sure enough, wow, we get these nice tight peaks. So, yep, and that value is right. And let me come down here. Yep, that value is right. And yeah, that's right too. So the more data we sample, the better off we are. We want our frequency we sample at to be an even number. And bonus, if our length happens to be a multiple of our sampling frequency, we get really good resolution. We get the best resolution. So if we were to sample at 1 kilohertz, ideally we would want to sample or we want to collect 2,000 data points. And there's one other thing, that is worth looking at, and that's we know our frequency. We know we want our frequency to be an even number. What happens if we make the length of our signal an odd number and we run that? Well, great. Here's our integer error again. These things get all monkeyed up, and this is kind of what we've seen before, is that these get messed up. So, okay, so what do we got? Well, we know that we need our length to be an even number. We really want our frequency to be an even number. If I change that and I make that 201, for example, we don't get that error, but things, they go poorly here in the plot. Things don't end up right because it doesn't have an even number of bins, right? Kind of screws up our division. So we know we kind of want our frequency and our length of our signal to both be even numbers, and the best resolution we're going to get is if our length is as long as the sampling frequency, or longer, ideally longer. And finally, the best case scenario, not required, but the best case scenario for us is that the length of our signal is some multiple of our frequency. So we've learned a couple of things. We've got some code here where we set these up. We know we can import some data. We know that when we're designing our experiment, we really want to make sure that our frequency, it helps that our frequency is an even number. It helps that the length of our data is an even number. We could fix that later on in Matlab if it wasn't. So that's handy. We would like our length to be, divisible by our frequency. If not, it's okay. It doesn't resolve quite as well, but it's okay. And we know that we can take an FFT using just the FFT command of some time domain data. We know it gives us this two-sided, this two-sided complex number. We know that we can get rid of the imaginary portion and just keep the real portion of this number simply by taking the absolute value and then dividing by the length to make sure the length of our signal, to make sure that it's properly scaled back. So, we can scale this right back down to the real data that we should have. And then we can get our single-sided by chopping off, the top half of this, starting with position 1, because we don't count 0, we don't count from index 0. So we start by chopping everything off from position 1 to half of our data plus one more spot so we can get half of our frequency. Our frequency is always one value less than the length we have in here. We know after that we can scale all of this. We have to double everything because the two-sided is half of our amplitude, and we know that that's also true only for our first frequency location, our first bin, our first value of frequency on up. We want to leave our our first bin in MATLAB speak, our first bin or our 0th frequency alone. We don't want to scale that. But otherwise, we scale everything else by 2. And then we know, last but not least, we need to tell MATLAB, what are the steps in frequency we have. So we're going to start with a 0 of whatever our length is, so 0/400ths in this case, times our frequency. So 0/400ths is 0. 1/400th of our frequency times the sampling frequency, so 1/400th of our sampling frequency, 2/400ths, 3/400ths, 4/400ths, all the way up until we get to half of that. So in this case, half, so 2/400ths, 400ths of our sampling frequency. And if we plot that, we go up to, let me rerun this because I changed some of our variables. So we go up to half of our sampling frequency, and the length of our signal, that splits this up into 400 chunks. That's what this is doing down here, splitting it up into 400 chunks. And there you have it. That is creating a spectrogram by using Matlab to take an FFT of a known signal. And all you would need to do is substitute in your raw data, figure out the length of your raw data, give Matlab your frequency, and you are done. This has been a very long video, and thank you for sticking with it, and have a good one.